Have you ever stopped to think about the invisible world of forces all around us? It's a world run by something called fluid mechanics, and it governs everything from the air we breathe to the oceans. These fluids shape our reality in ways that are, well, incredibly powerful, and once you get the hang of it, surprisingly simple.
I mean, it all sounds a bit like a magic trick, doesn't it? A tiny push lifting a car? A massive steel ship just floating there? How is that even possible? Well, believe it or not, these are the exact mysteries we're going to solve today, just by breaking down the basic rules that all fluids have to play by.
So to get to the bottom of all this, we've got to start with the absolute basics. First things first, what in the world is a fluid? The answer is probably way simpler than you think.
The key phrase right there is anything that can flow. That's it. So this means we're not just talking about liquids, like water. Gases, like the very air that's all around us right now, they're fluids too. And once you get that, you've taken the first big step to understanding everything else. Okay, next up, let's talk about a core property of every single fluid: density. Just think of it as how much stuff is crammed into a certain amount of space. A block of lead is way, way denser than a block of wood of the exact same size. This one idea is the real key to why some things float and other things sink.
We have all felt this. You're in a house and the warmest air is always up near the ceiling, while the chilly air kind of settles down by the floor. Why? Because when you heat air, its little particles spread out. It becomes less dense, and that causes it to rise. It's a perfect everyday example of density in action.
Okay, so we've got density down. Let's move on to our next big concept: pressure. And this is where things get really cool, because this is where we start to see how a tiny little push can be multiplied into an absolutely incredible amount of force.
The secret here is all in the relationship between force and area. See, pressure isn't just about how hard you push, it's about how concentrated that push is. And that simple relationship has some seriously surprising results. This is the secret sauce. If you can shrink the area you're applying a force to, you can make the pressure go through the roof, even if the force itself stays exactly the same.
Let's make this really simple. If you push on your arm with the palm of your hand, not much happens. But what if you apply that same exact force with just the tip of a pen? Whoa, that high pressure is going to be a lot more noticeable, right? Same force, different area, totally different pressure.
And this brings us to the absolute genius of Blaise Pascal. His principle basically says that if you've got a fluid sealed up in a container and you apply pressure to one spot, that pressure doesn't just stay put. Oh no, it gets transmitted without losing any strength to every single point inside that fluid. And here it is, the solution to our first mystery. In a hydraulic lift, you apply a small force to a small piston, which creates pressure. Now, thanks to Pascal's law, that exact same pressure travels through the fluid to a much bigger piston on the other side. And since pressure equals force divided by area, that same pressure acting on a larger area creates a much, much larger force. It's a brilliant trade-off. Sure, you have to push the small piston a long way to make the big one move just a little, but in return, you get this massive multiplication of your original force. In the example from the source material we're looking at, the math works out to this. Your small push gets multiplied 36 times over. You push with the force of 1, and the machine pushes back with the force of 36. And that's how you lift a car with just a tiny push. It's absolutely incredible. All right, mystery number 1 is solved. Now for the second one, how does a gigantic ship made of super dense steel that should definitely sink somehow manage to float? The answer lies in another one of these foundational principles. This is it, the legendary eureka moment. Archimedes figured out that when you put something in water, the water pushes back. And the power of that upward push, which we call the buoyant force, is exactly equal to the weight of the water that the object just pushed out of the way. So think about this little experiment. An object weight in the air is heavier than it is when it's weight in water. That lost weight? That's the buoyant force. And if you could collect all the water that spilled out, you would find its weight is a perfect match to that buoyant force. And here we go, the answer to our second mystery. A solid ball of steel sinks like a rock because it's dense and doesn't move much water out of the way. But if you take that exact same steel and shape it into a huge, hollow hull, its giant shape displaces an enormous amount of water. And if the weight of all that displaced water is equal to the ship's total weight, then the upward buoyant force perfectly cancels out the downward pull of gravity, and the ship floats.
It's not about the material, it's all about the shape.
So far, we've only been talking about fluids that are just sitting still. That's called statics. But things get even more interesting, and maybe a little crazier, when fluids start moving. Let's dive into the world of fluid dynamics.
When fluids get going, they usually move in one of two ways. You've got laminar flow, which is all smooth and predictable, kind of like honey pouring from a jar. And then you have turbulent flow, which is chaotic and messy like a raging river. Just knowing that difference is key for what's coming next. Now, this is one of the most important ideas in all of fluid dynamics. Bernoulli found this inverse relationship between a fluid's speed and its pressure, and it's a little bit of a mind-bender. Where the fluid is moving the fastest, its internal pressure is actually at its lowest.
This diagram of a Venturi tube shows it perfectly. See, the fluid gets forced through that narrow part in the middle. To get the same amount of fluid through a smaller space, it has to speed up. And just like Bernoulli predicted, right there where the speed is highest in that narrow section, the pressure is lowest. This single effect is the secret behind everything from perfume bottles to airplane wings.
So let's recap. We've hit on density, Pascal's law, Archimedes Principle, and Bernoulli's Principle. And these aren't just some abstract ideas from a textbook. They are the absolute bedrock of modern engineering. And it's cool to see how these big ideas all connect. Take Torricelli's theorem, which tells you how fast water will shoot out of a hole in a tank. Turns out it's really just a simplified special case of the much bigger, more powerful Bernoulli's theorem. It all fits together. The principles we've talked about today are literally everywhere. The hydraulic lift in your mechanic's garage, that's Pascal's law. Every single ship floating on the ocean, that's Archimedes' principle. And the lift that makes an airplane fly is all thanks to Bernoulli. The air on the curved top of a wing has to travel faster than the air on the flat bottom. Faster air means lower pressure on top, and the higher pressure below pushes the whole plane up. These aren't just theories. They're the invisible forces making our modern world work. The world is just full of these hidden fluid dynamics. So now that you know the secrets of pressure and buoyancy and flow, I challenge you, look around. Where can you see these principles in action? You might be surprised by how much of this invisible world you can now see.